Hello everyone, welcome to Programming and Optimization with Intel Architecture, the Hands-on Workshop Series, Day 7. We are in Day 7, today is Thursday, and we are going to discuss optimization of multi-threaded applications. If you would like to get the slides that I'm using or view recordings of earlier presentations, you can click this link, or you can go to colfaxresearch.com in your web browser and start here, training, web-based, and there you have it, September 9 workshop. That's the page for it. From this page you can download slides, code that we are using for hands-on exercises, and view recordings of earlier presentations. For more information, you can refer to our book, Parallel Programming and Optimization with Intel Xeon Phi Coprocessors, available at this URL. The book explores all the topics that we talk about in the training and more, plus all the exercises that we're dealing with come from this book. Remote access will be useful for the second hour of this presentation, where we go to the hands-on presentations, to the hands-on exercises. If you have remote access and have any trouble using it, let us know, we will help you. If you don't have remote access, I may have a few seats available today, so send me a message in the questions box. This course, for participating in this course, you can get a certificate of accomplishment in the fundamental level, and you have to attend 6 or more sessions out of 10. Visit us at colfaxresearch.com. This is a great resource for free information on parallel programming with a focus on programming Intel Xeon Phi coprocessors. What you can find at Colfax Research includes case studies, presentations, tutorials, video courses. We have just posted a video course. One of the video courses is based on a workshop like this, and another video course doesn't have the hands-on part, but it is a very concise and detailed description of nearly the same material, also available with subtitles. So I'm going to do a quick review of some of the material that we covered in earlier sessions, and I hope it will be enough to refresh your memory and give you enough material to follow along with today's presentation. We are talking about Intel architecture, focusing on 2 platforms, Intel Xeon processors and Intel Xeon Phi coprocessors. They are both highly parallel processors with tens of logical processors and vector units inside of every core. But Xeon is more general, is more versatile. It can compensate for memory access pattern that is suboptimal. It can work relatively well with poorly parallelized applications. On the other hand, Xeon Phi is more specialized. It needs highly tuned code, but if you give it highly tuned code, it will perform better than the Xeon of the comparable cost and power. At the same time, throughout this course, I'm demonstrating that you can write a single application, single code, which will work well on Xeon Phi coprocessors and on Xeon, as long as the problem, as the numerical algorithm allows that. Even more, when you parallelize this code, in OpenMP, MPI, and using automatic vectorization, you can expect it to perform well on both platforms. Today we will talk about optimization of multi-threaded applications. And this discussion will apply both to Xeon and Xeon Phi. In the context of optimizing multi-threaded applications, it is useful to think of Xeon or Xeon Phi as a symmetric multiprocessor. You have many cores. Each core can run an independent stream of instructions from every other core. At the same time, cores have access to the shared memory, and this memory is cached, and caches are kept coherent across different cores by hardware. So when you want your application to use multiple cores, this is not automatic. You have to use multi-threading. In other words, a single process will spawn multiple streams of instructions called threads, which will all share the same memory but be able to utilize the resources of different cores. The multi-threading framework of choice for this course is OpenMP, and we discussed it in session number 4. So if you've missed session number 4 and you're not familiar with OpenMP, you can go to the course page later on, and you can watch session number 4, which is a crash course on multi-threading with OpenMP. Multi-threading must coexist with vectorization in every core, and vectorization is what we discussed in the previous session and also in session 3. To coexist, usually multi-threading and vectorization must work on different levels of parallelism inside of your application. So some applications are naturally composed of 2 loops, and normally you would try to parallelize the outer loop, the outermost loop across threads, and the innermost loop across vector lanes. Sometimes you have just one loop in your application, and if everything is really data parallel, then you can combine multi-threading and vectorization in one loop. Sometimes this is automatic. Other times you may need to use programming techniques such as strip mining to expose vectorization opportunities to the compiler. So today we are going to talk about optimization of multi-threaded applications. And this is part 1 out of 2 because this is a really big topic. In one of the earlier episodes, I've proposed this optimization roadmap. When you work on an application, you should address these 5 areas: performance on the scalar level, performance on the level of vectors, performance on the level of multiple cores, optimization of memory access, and optimization of communication. So we are talking about this topic, and even though in a real-world application, whatever you do will probably affect several areas at once, we tried in this course to come up with exercises that are really targeted to a specific topic of optimization. Why is it difficult to not just have threads, but also to have them operating efficiently? One of the biggest difficulties is just having enough parallelism in your application to keep all cores busy. And if you already dealt with parallel applications before on processors with just a few cores, this is maybe quantitatively different from having a processor with tens of logical processors, or having a Xeon Phi coprocessor with hundreds of logical processors. So you have to have enough parallelism to keep all of these logical processors busy. Another problem with parallelism is synchronization. The more threads you have, the greater is the penalty that you pay for any form of synchronization, mutexes or barriers in your code. Mutexes serialize the application, and they are especially painful on Xeon Phi with many cores. So we have to control synchronization, and I will demonstrate a parallel pattern today that is useful in many cases to do just that. Also, in real-world applications, you may discover that per-thread memory overhead is a difficulty, because if you optimize your application for a CPU, which has, well, tens of threads, but possibly tens or hundreds of gigabytes of memory, then when you move to Xeon Phi, you have more threads and less memory, only up to 16 gigabytes. So sometimes you have to start thinking of how to be more economical about per thread memory overhead so that you can fit all threads in memory. Usually, multi-threading optimizations will overlap with optimizations in other areas. For example, locality of memory access is related to thread affinity, which we will discuss tomorrow, but this is actually a memory optimization. Also, making vectorization coexist with multi-threading or balancing the parallelism between them is what we will discuss today. And this overlaps with the optimization of vectorization. So I will do a very quick review of OpenMP. I'm sorry, just the functionality and without much detail. So OpenMP is a parallel framework that allows you to create multiple threads within a process. To create multiple threads, you can use the directive pragma OMP parallel, and you have to compile your application with the argument QOpenMP. When you run, by default, OpenMP will create as many threads as many logical processors your CPU has. But you can control this number by setting the environment variable OMP num threads to an integer. In OpenMP, all variables declared before the parallel region by default will be shared between all threads. If this is the behavior that you want, you don't need to do anything, but sometimes you may want to make some variables private to each thread, and you can use either the clause private in pragma OMP parallel, or if you're using C and C++, you can declare the thread private variables inside of the parallel region, and they will automatically become parallel to each thread, because the code in the scope of pragma OMP parallel is executed by every thread. The power of OpenMP is not only in that you can create threads, but in that you can distribute work between them. For example, if you have an application based on loops and different iterations in these loops can be executed independently, there is an OpenMP directive which will take this loop and distribute it at runtime across different threads. The directive for it is pragma OMP4, and you can combine it with parallel in one line, so it would say pragma OMP parallel 4. And of course, you can use all the clauses of pragma OMP parallel in this case, as usual. What will happen is different iterations will run in different threads, but at all times there will be only one iteration running per thread, so you will not have thread contention. Ideally, you want many loop iterations for the amount of threads that you have. Millions of iterations is just fine. They will not oversubscribe the system. OpenMP will take care of scheduling. Scheduling of iterations in OpenMP can be controlled using the clause schedule, and there's 3 scheduling modes that we discussed earlier: dynamic, guided, and static. In OpenMP, the biggest difficulty is not creating threads or making all these threads do useful work, but rather controlling the correctness of this work. And we have discussed race conditions in episode number 4, and today we will revisit them and learn a parallel pattern that is very useful for controlling race conditions without really compromising performance. And as usual, all the optimization topics that I discuss will be discussed based on an example. The example that I want to use for the following discussion is actually the example with which we finished the previous presentation. This is a binning microkernel. We have a synthetic application, but it is actually representative of applications of workloads that occur in statistics, in particle physics simulations, and in Monte Carlo models. What we have is we have a large array age. It has hundreds of millions of elements, and these elements are ages of different people from 0 to 100 years. N is the size of this array, And what we want to compute is we want to compute how many people we have in the age group 0 to 20 years, 20 to 40 years, and so on. So the group width is 20, and we want to fill in this array hist. Hist 0 will be the number of people in age group 0 to 20. Hist 1 will be the number of people in age group 20 to 40 years, and so on. And it is not difficult to do if you are not concerned with performance. You just write one loop that goes over all people. For each person, it takes the age, divides it by the group width, converts into an integer, and this is the index in the histogram which you have to increment. Of course, there is no bounds check in this application, but we assume that the data is preconditioned somehow. There is no parallelism in this implementation. The compiler will refuse to vectorize this loop, and we discussed in the previous session why. Also, there is no thread parallelism because, as you can see, we are not using OpenMP. So the performance of this application will not be satisfactory if this is a performance critical part of your, say, Monte Carlo simulation. In the previous presentation, we have discussed the implementation of vectorization in this code. And that's what we had to do. We strip mined the loop, meaning we introduced a new variable, veclen. We chose it equal to 16. And what we did is we rewrote the single loop in the application so that the outer loop iterates through all people with a stride of 16. And then we have an inner loop that goes through these 16 people in that block and computes the number of age groups for them. And the reason we did strip mining is so that we can split off the calculation of the index from the increment of the histogram. So actually inside of this big loop in II, we have two loops of length 16. One computes indices and the other uses these indices to fill in the histogram. This first loop is going to be vectorized by the compiler. The second loop is going to be scalar, but this is just the nature of the workload. There is nothing we can do about this. So now we have a partially vectorized calculation. We have data parallelism. And also because we used the reciprocal of the group width instead of dividing by the group width, we also improved some performance on the scalar level. So we touched two areas of optimization in this code. Now let's touch the third one, which is multi-threading. And because now we have naturally two nested loops in our application, it would be very straightforward to say, well, I have the outer loop, I will distribute this loop across threads. And then I have the inner loop, it will naturally coexist with multi-threading, because in this loop I have vectorization. I'm sorry, it will coexist with multi-threading because it is the inner loop, and we will naturally have vectorization in the inner loop and multi-threading in the outer loop. So let me just slap on Pragma OMP parallel 4 and see what happens. Yes, I forgot that I have one more slide that demonstrates results of the previous calculation. Sorry, let's roll back. Forget about multi-threading. The slide shows the performance on the host system and on the Xeon Phi coprocessor before optimization and after optimization. So the vectorized calculation was performing something around 1 billion operations per second on the CPU on one core, and 1/8 of a billion operations on Xeon Phi. And I'm always comparing one Xeon Phi coprocessor with a dual socket Intel Xeon E5 2697 V2 high-end processor, so that I'm comparing two devices of similar thermal design power. So let me try to just slap on Pragma OMP parallel 4 on the outer loop, and This will produce multi-threading. This seems easy, but it doesn't work very fast, but most importantly, it produces incorrect results. The results are incorrect because, as we discussed earlier, there is a race condition in this line. What does this mean? In this line. What does this mean? Hist is the output array. It was accepted by my function somewhere up here as the input argument. And because it was declared before the parallel region, it automatically becomes shared across all threads. So what's happening here is each thread will have its own index, and each thread will pick an element in the shared array hist, and it will try to increment the element at that index. Sometimes, actually most of the time in this application, more than one thread will try to increment the same index at once. And incrementing is actually 3 operations. You have to read the variable, you have to add 1 to it, and you have to write it back. So it's actually 3 operations. When multiple threads do it, you are not guaranteed the order in which these threads do it. For example, 2 threads may read the same value of the old element, increment it, and write it back. And in this way, I will lose one of the increments. And this is what is actually happening here. I could try to protect race conditions. We discussed in session number 4 that there are constructs called mutexes, mutual exclusion conditions in OpenMP, that allow me to protect a part of the code or a memory location from concurrent accesses. So I could use Pragma OMP Atomic, which is a lightweight mutex for the increment operation. What it will do is it will make my program produce correct results, but we will see that the performance of this program is actually worse than the performance of a serial application because I have so much synchronization. And each synchronization event is a performance penalty because for a brief moment of time, I have fewer than 240 threads working on Xeon Phi. And if these moments occur too fast, then by Amdahl's law, the overall performance of my application goes way down. Instead, I will use a pattern that we also saw in the session in the crash course on OpenMP in session 4. By the way, I want to address, before I keep going, I want to address a question that just came in. The question is the index array declared again on each outer loop? How much is the cost or overhead of that? And I have an answer to that. In a serial application, well, that's what would be happening. This array will be created and destroyed in every iteration. And because it is created on the stack, it is actually very fast. But because this calculation is going to pass through the vectorization, through the automatic vectorization functionality, there is actually no penalty for doing that. In fact, the compiler will be able to even eliminate the creation of this index and replace it with just having a vector register here. So because this array has only a length of 16, you actually don't need a storage for this. I think the compiler is able to realize it, and we have traced it through the assembly. But a related comment that I wanted to make to this is that the Intel compiler really seems to like short-lived variables. So I've made many experiments, and in my conclusion was that usually declaring a short-lived variable is better than declaring a long-lived variable outside of the scope of a loop, because the compiler is better able to understand that this is a transient variable and maybe even eliminate memory allocation for it in the first place. So I'm pretty sure that this is a good solution. in the hands-on part, we can try to move this out and see what happens. Okay, so back to optimizing the parallel pattern. The problem that we had is race conditions. Different threads were trying to modify the same memory region, and this causes incorrect results. If I include the atomic construct, it destroys performance. So instead, what I will do is I will use thread private variables. This is an illustration of a different workload, but it is straightforward to understand what's happening here. I'm trying to add integers starting from 101 through 600, and I'm doing it in 5 threads. So I have a common container, x equals 0, and to do this kind of operation in parallel, I will create thread private containers, x1, x2, x3, x4, and I will do additions on thread private containers. So there is no race condition here because different threads are working on different memory regions. After that, when I'm done with 100 iterations, I will run a reduction where I will add thread private partial sums to the global sum, and I will protect these increments with atomic operations. So in fact, there will be some serialization of my application, but the degree to which I'm serializing is much less than if I just used atomics here. This is what it will look like in code. I declare a parallel region, and then I declare another variable inside of this parallel region, hist private. It has the same shape as the global container hist. Actually, let me remind you that this shape is only an array 5 elements long. Because I'm declaring this variable inside of the parallel region, it will automatically become private to every thread. So if I was using Fortran, I do not have the ability to declare variables in the middle of a function in Fortran. I would have to declare it at the beginning of the function and then use the clause private. So I would say, have something like pragma OMP parallel private hist private. Notice that I'm initializing it in the parallel region, and then what happens is I run my loop. But here, where I used to have the race condition, instead of using the shared container, I'm going to use the thread private container. So I'm just accumulating whatever data this thread is processing at runtime. Excuse me, at the end, I will have to reduce, in other words, to aggregate the results of individual threads into the common shared container. Because the shared container is an array, I will have to run a loop, and inside of the loop, for every scalar in that array, I will run an atomic increment. This is much more economical than doing reduction here, because if I did pragma OMP atomic before line 12, I would run it n times, where n is in the hundreds of millions. Whereas here, I'm just doing m times the number of threads, which is maybe 1,000 atomic constructs. So this is a parallel pattern that we saw once in session number 4, and we will see it over and over again. This is a very common parallel pattern. We call it reduction with thread private variables. And it allows you to be economical about how you use synchronization, specifically mutexes. Something else to note about this pattern is that the reduction is done with a linear algorithm. So if I have n threads, I have O of n synchronization events. It is possible in principle to run reduction with a tree algorithm, where instead of O of n events, I will have O of log n events. It should not matter as long as the bulk of the calculation is overwhelmingly more expensive than the reduction. If it does matter, then you can look into tree reduction algorithms. Performance results speak for themselves. Again, I'm showing the performance on the host system and on an Intel Xeon Phi coprocessor. And my baseline in this case is the code that has been vectorized, but uses just one thread. So 1 billion operations per second on the host, 1/8 of that on Xeon Phi. These two bars, which you can barely see, show the performance results when I was not economical about mutexes. That's where I just put pragma OMP atomic before the race condition. As you can see, performance dropped on both platforms instead of increasing, even though I had a parallel application. Finally, the third set of bars is what we achieved by using reduction with thread private variables. On the host, performance went up by a factor of 10. On Xeon Phi, it went up by a factor of around 100. So this example with binning, I really like because I can demonstrate a lot of different things using it. And what I've just demonstrated is using reduction with thread private variables to be more economical about using mutexes. I'm going to use this example once again to discuss another topic of multi-threaded application optimization, and that topic is false sharing and its elimination. So first, let me describe what false sharing is. When most processors, including Xeon and Xeon Phi, access memory to read or write, for example, one floating point number, they actually read more or write more than this floating point number. They read or write an entire cache line. A cache line is the minimal amount of memory that you can move between RAM, between the system memory and caches, or between different levels of cache, or between caches and cores. This amount of memory is 64 bytes in Xeon architecture and in Xeon Phi architecture. So whenever you read or write one floating point number in single precision, you're actually moving 8 floating point numbers in memory. This is economical because if your application has unit stride access and you have used one number, you will likely use nearby numbers. So you will have just one memory access and you will use this number 8 times in cores. This is how you automatically increase the arithmetic intensity of your application. But sometimes this can be a problem. And this can be a problem when you have a parallel application. As I mentioned, in Xeon and Xeon Phi architectures, caches are kept coherent across different cores by hardware. And what it means for parallel applications is that when one application modifies one number in memory, the entire cache line must be locked and propagated across all other caches that have this line. So when another thread is trying to modify a different memory location, which is in the same cache line, it has to wait. This is somewhat similar to race condition in that different threads are accessing memory locations that are related to each other. But unlike with race conditions, false sharing does not cause incorrect results. It only causes performance loss. And this is a natural property of coherent caches. This is what you have to pay for having the convenience of doing fewer memory accesses than you would otherwise do. False sharing may occur in many situations, but I will discuss one situation that I have personally encountered, and I have seen it encountered in some other user applications. This is when you try to be very economical about your thread private variables. So what we did in the previous implementation of the binning code is we created a thread private container for each thread to operate on. This thread private container was allocated on the stack of each thread. So thread private containers for different threads were actually really far apart in memory, because the stack of each thread, well, is a few megabytes at least. I will try to use the same strategy as before, but I will change the data layout. Instead of having thread private containers, I will have one global container, but it will be a two-dimensional container with compartments for every thread. So see, I have two dimensions. One dimension has as many elements as I have threads, and the other dimension has as many elements as my original container hist. So this is on Xeon Phi 240, and that is, in my problem, 5. So I have in memory, in C and C++, such two-dimensional arrays are row major. So these 5 elements will be sequential in memory. Then the next element here follows immediately in memory. The next element follows immediately in memory, and so on. There is a certain advantage to having such a container over having thread private containers. For instance, when I finish the parallel loop and I exit the parallel region completely, I still have the data collected by every thread. And I can use this data for many purposes. For instance, I can run some statistical analysis on this data to analyze my load balance. Alternatively, I can use this data to analyze, again, statistically analyze, for example, random numbers that I generated in a parallel application. In a parallel application, do I have cross-stream correlation between them or not? Finally, I can use this container to maybe take this data to another function, which will run a tree reduction algorithm. So maybe I will use it to run an economical reduction algorithm somewhere else. So I like the idea of doing that. And when I do that, what I will have to do is, when I have my potential race condition, I will make each thread write into its own compartment. So thread number 0 will always write to compartment number 0. Thread number 1 will write to compartment number 1. So they will all write to different memory regions at the same time. Yes, which means that there are no race conditions, and then I can finish the parallel region and do the reduction. But here's the problem. My array is relatively small. It only has 5 elements. A cache line is 64 bytes. So a cache line fits 3 containers plus a part of another container. So each cache line has parts of 4 containers, which means that when thread 0 is writing here, thread 1 is writing there, thread 2 is writing there, they are all modifying different data, but this data resides in the same cache line. So while thread 1 is doing its update, thread 0 is doing its update, threads 1, 2, and 3 have to wait. A really easy solution to this problem is padding, where I will add to the inner dimension of my array some elements that will never be used. They are just there so that thread 1 has its own cache line to write into thread. The same for thread 0, thread 1, and 2. In code that will look like this, I'll choose the number of bytes to which I want to pad, and then crunch the math, convert it to elements, see how many bytes I have to add, and the inner dimension I declare to be slightly larger. Here are performance results, which are pretty insightful, I think. My baseline is the performance of the optimized code with multi-threading on Xeon and on Xeon Phi. So this is what I started with. I used thread private containers. And then I did this implementation with one global container with compartments for different threads. The performance, instead of staying the same, dropped by more than a factor of 10 on the host system and almost a factor of 10 on Xeon Phi. Then I implemented padding, and first I padded to 64 bytes. And see what happened to performance on Xeon Phi. It bounced back to the original level. So on Xeon Phi was pretty happy with a padding value of 64 bytes. But Xeon actually was not pretty happy with that. It was happier with greater alignment, and finally it only recovered when I padded to 256 bytes, meaning that different threads are writing at least 4 cache lines apart from each other. I attribute this to the prefetching functionality. Prefetching is functionality found in processors, once again, to automatically speed up your memory access. And what it does is when a processor accesses one cache line, the cache will think, oh, okay, this guy is using this data, so he will likely use the data nearby in the next cycle. So let me give him not one cache line, but 4 cache lines. In fact, prefetchers can be pretty sophisticated. They can train to the memory access pattern that you have. But in the application that we had, what prefetchers did is they actually caused false sharing when 2 threads were writing into nearby cache lines. So even the nearby cache lines had to be locked because of the prefetching functionality. Only when I padded to a sufficient distance did I recover the performance on Xeon. So this is something to keep in mind whenever you allocate memory for thread private containers to deal with race conditions, that you may need to do some padding to avoid false sharing. So far we have discussed 2 topics of performance optimization in multi-threaded applications. One was being economical about mutexes. The other was dealing with false sharing. For both of these examples, we used the binning workload. And I've actually used the binning workload earlier to demonstrate strength reduction and strip mining. So I think it's time to put this workload to rest and to switch to another example. So let's forget about histogram and binning and focus on another workload. It looks like this. I have a matrix of size Mij, and what I want to do is I want to sweep in the unistride direction along this matrix. I want to sweep from column 0 to column n. I want to add all elements in row I, and I will want to report the sum of all elements in row I. You can think of this as a very primitive stencil. Maybe this is a one-point stencil. And in fact, even though this is a synthetic application, what I will demonstrate, we will find that this is a very generic situation. Let's focus on specifics and then you will understand why. I'm assuming that my matrix is very weirdly shaped. It only has 4 rows, so M is only equal to 4, but the inner dimension is very large, in the hundreds of millions. Well, of course, this is chosen to exaggerate the problem and to demonstrate clearly the performance benefits of the optimization technique that I will demonstrate. But we will find, for example, in session 9, that we encounter situations just like that, doing memory optimization. When you do loop tiling, oftentimes you thin out the outer loop so much that you actually find yourself dealing with something like that for an outer dimension of 4 and the inner dimension which is very large. So what I'm going to demonstrate uses this simple example just to keep things understandable in the format of a training, but this is a very generic problem. I will start with an implementation which this time is highly parallel. I will use Pragma OMP Parallel 4 to parallelize the outer loop across threads, and notice that there's the problem. I only have 4 iterations here. And I will use another loop to go through all of the matrix elements and add them together, and this loop will be vectorized. This looks like a pretty good implementation, and it would have been good only if M was not so small. But M is small, it is only equal to 4. So what will happen is I will parallelize this loop across 4 threads. Each thread will have a lot of work to do, but all of the other threads in my code will not be doing anything useful. To diagnose this situation, I could potentially use vTune Amplifier XE, a performance analysis tool that we will discuss in session 10. And it would show me that 4 threads have these brown timelines, they are working, but all other threads have orange timelines, meaning that they are spinning. How can I fix this situation? Well, one approach that seems natural is to realize I have little parallelism in the outer loop. I have a lot of parallelism in the inner loop. So why don't I move Pragma OMP parallel 4 into the inner loop? We will see that this is not such a bad strategy. Specifically on Xeon Phi, it achieves nearly 80% of the optimal solution that I will demonstrate later. But on Xeon, it only achieves 50% of what we could do. The reason why it is not optimal is there's 2 reasons. One reason is that, well, first, we do not expose the entire amount of parallelism to the compiler. We are only exposing 1/4 of the parallelism. Another problem is that this parallel region will have to start and stop parallel loops as many times as I have iterations here. So 4 times I will have to start and stop parallel loops, which is suboptimal. How about another strategy? OpenMP has functionality called loop collapse. The way it works is if I have 2 closely nested loops, one inside of each other, I can add the clause collapse to, and effectively this will tell the compiler that I want to parallelize across not the iteration space of the first loop, but across the dot product of the iteration space of the first loop and the second loop. So instead of it parallelizing across m iterations, I will parallelize across m times n iterations. I could do it potentially by hand like that. I could iterate from 0 to m times n and then map this new index c to I and j. So this is what loop collapse does. Let's see if I can use it in my application. Well, to use loop collapse, I will have to make my application slightly more complex. Instead of having a thread private container which is a scalar, I will have to use a thread private container which is a vector, because now different threads will have different values of j. And then I will type Pragma OMP4 collapse 2, use these 2 loops, and do all the other things that I have to do. This seems like we are on the right track, but unfortunately, the compiler will not be able to make vectorization in this loop to coexist with multithreading. This may be something that the compiler could do sometime in the future, but not in this implementation. So we need to help the compiler. We need to expose vectorization opportunities to it. And this is when, once again, we will use the strip mining technique. The strip mining technique involves transforming one loop into 2 nested loops. I will create a compile time constant, which has to be a multiple of 16. I actually had to do some experimentation to find the optimal value and found it to be around 1000. And then instead of 2 nested loops, I have 3 loops. One in I, unmodified, one in j. Actually, in jj, it goes from 0 to n, but with a stride of 1024. And then inside of that loop, I have one loop that goes with unit stride across these 1024 elements. So now, this is the innermost loop, so I can expect the compiler to vectorize it. And the outer 2 loops can be collapsed to expand the amount of parallelism that is available to OpenMP. So now I have sufficient parallelism because I moved some of the parallelism from the innermost vectorized loop to the thread parallel loop. Of course, when I did that, I had to do some tuning here. I had to create this thread private variable, which is an array, because different threads may be working on the same value of j. And I had to do this reduction using atomics at the end. If I ran this code again through vTune, I would see that my timelines are mostly brown, but all of the threads are working. They are mostly brown because this is a bandwidth bound calculation, and naturally I don't have a very high instructions per cycles ratio. So this is the performance measurement. Again, on the host system and on a Xeon Phi coprocessor, I'm measuring performance in gigabytes per second read from matrix M. When I started, Xeon was not doing so poorly, and Xeon Phi was pretty miserable. I'm measuring bandwidth in gigabytes per second so that I can compare it against a known upper bound for this metric. The upper bound will come from the stream benchmark of memory bandwidth, and specifically for the copy test, the stream benchmark on the host gives me around 90 gigabytes per second, and on Xeon Phi it gives me around 180 gigabytes per second. So here I'm operating at about 50% of what I could be doing. There I'm operating at about 5% of what I could be doing. Then I tried to parallelize the inner loop. Performance did not change much on the host, but it improved quite a bit on Xeon Phi, but I can still do better. So I tried to do loop collapse. On Xeon, it didn't change results much, but on Xeon Phi, the performance collapsed again because I lost vectorization. And finally, when I combined strip mining and loop collapse, performance on the CPU improved by a factor of 2. And on Xeon Phi, it is slightly higher than the stream copy benchmark, which is not surprising because the copy benchmark reads and writes, and I'm only reading. So this is a demonstration of how to deal with insufficient parallelism by moving parallelism from vectors to threads. Sometimes you may need to do the opposite. This is a case where maybe your threads are too lightweight and the thread scheduling overhead is too high. Sometimes, if you have 3 levels of parallelism, you have vectors, threads, and scaling across a cluster, then you may have to think of moving parallelism between MPI processes and OpenMP. And usually, if your application is centered around loops, then the strip mining technique is what you can do to easily move parallelism, and then tune it by choosing the strip width, tune how much parallelism you retain at different levels. So today I discussed a few problems that you can encounter with multi-threaded applications, and demonstrated some of the ways to deal with them. This is not the end of the discussion of optimization of multi-threaded applications, but we have enough information to go on in the practical part. So if you have data races, you have to use mutexes to resolve data races, but you have to be economical about mutexes. You may not use them in the innermost loops. A better idea is to use thread private storage and only use mutexes for reduction. If you are too economical about your thread private storage, you can run into false sharing, and you can resolve it with padding. And on Xeon, you may need more padding than on Xeon Phi because of the prefetching functionality. Finally, I talked about not having enough parallelism on the level of threads, and demonstrated using strip mining and loop collapse to reallocate parallelism from vectors to threads. At this point, I am ready to move on to the practical exercises and demonstrate what I've just done live. But tomorrow we will continue talking about thread optimization of multi-threaded applications and talk about thread affinity control, and also loop scheduling. So we will begin our usual 2-minute break, and during this break, please connect to your remote access servers. I've noted remote access requests that have come in. I will connect myself, and if you don't have remote access, then stay online, because in the second hour you will be able to follow along with me. So see you in 2 minutes. So welcome back, and let me try to do something with my sound. I think this should be good. I had a comment about sound, but I think now it is not too loud and not too soft. If anyone has issues with the sound, please type in the questions box. If the volume is lower than before, maybe you can adjust it up. But I think I was going over the limit of volume in the previous sound setting. Okay, so I am connecting to my system using NoMachine, and fortunately I have everything open from yesterday. So let's go full screen. If you're using NoMachine, remember to click Resize Remote Screen when you go full screen or expand the window, and then you should see it there is echo in the call feature. So if you are connecting from a telephone and you are hearing echo, uh, if you are on the speakerphone, no, this cannot happen. Let me try to do something. Um, the person who commented about echo, can you check again? Do you still have echo? Yeah, somebody else responded that no echo. Well, let me start talking while I wait for the response. Okay, so sound is fixed. Great. Let's keep going then. So yesterday we started in lab 404, and this lab contains the histogram calculation example. In this histogram calculation example, we were working with the file worker.cc, and I believe that I also used to have the log open. So let's look at the log. No, 404 log. There we go. So this is the log of what we've done. The original calculation, this is the performance in billions, in values processed per second. Then we did strength reduction. We used to have a division by the group width here, but remember we introduced this new variable 1 over the group width. And finally, we did strip mining. For strip mining, we chose this variable, and it allowed us to split this loop, which is vectorized, from that loop, which is not vectorized, but it should be um, straightforward. So if you've missed that presentation, you can refer to the very end of the recording for session number 6. Yes, number 6. Okay, so at this point we have an application that has vector data parallelism, so vectorization, but no thread parallelism. Let me run it again. I just realized that if you're trying to follow along with me, it may be a little difficult because you may not have the code that I am dealing with. So let me actually simplify everybody's life and just get this answer from the solution. So if you're trying to follow along with me, let's run this command. Copy solutions instruction 02 worker.cc. This file we are going to copy into the current folder. Just overwrite. And I will reread my file. As you can see, it is essentially the same code. It is slightly longer. What I'm doing here in the solutions is I'm handling the situation where n may not be a multiple of 16. So I have one loop which does the bulk of the work, and then another loop is the remainder loop that finishes things off. So I don't have to worry about this loop, it only does up to 16 iterations. But I want to focus on that loop. And let me run again to make sure that I get the same performance. Is it the same? Well, slightly better. I think it will be close enough. And what did we log? Ours was slightly faster. Do we have an explanation for that? Yes, so our implementation was slightly faster because I took advantage of the hint that I discussed in the previous session, pragma vector aligned. So once I do that, I will get the same performance as before. So this hint, a reminder, tells the compiler that it is free to not implement a peel loop because I guarantee that my data begins on an aligned boundary. And that doesn't seem the same, does it? Let's see what else I may be missing. Is the make file the same? Well, yes, I am using the same make file, but is that make file the same? This is the same. And as for main, okay, I allocate everything aligned. Something I did in the previous code is I think it looked like this. Does it make a difference? I hope not, because I would have no explanation for this. No, this doesn't make a difference, and maybe I used something else here, like this. Hopefully that also doesn't make a difference. This is strange, but let's then go with what we have. As I noticed earlier, declaring this inside of the loop seems to be good, and I can move it outside of the loop, and I don't think it will change the results. Yeah, same results. So I will just keep it inside the loop for more convenient programming. So I will want to parallelize this loop, and let me try to just parallelize this loop with OpenMP. Pragma OMP parallel 4. Pragma OMP parallel will create threads. 4 will distribute loop iterations across threads. So I run the code again. And it's not going to take very long because I think it will bail out immediately. Yes, it did one iteration and immediately it's telling me that the results are incorrect. Also, the performance is not very good. So let's record this fact, and the performance was 6.6 E7. And I will put incorrect in all caps. I will not even measure the performance on the host CPU. The results are incorrect. I know why. Because here I am using the shared container, and this is causing a race condition. So let me try to protect this race condition. I will introduce I will first do what I can do in parallel, and then I will put pragma OMP atomic to protect this increment. Let's see if it makes my results correct. And fast. So the results are correct, I don't get any complaints, but the performance is poor. The performance on the CPU is only 50 million operations per second, so it dropped more than an order of magnitude. On Xeon Phi, I think it will be even worse than that. How many times am I running this atomic operation? Obviously as many times as I have iterations in this loop. Essentially, I'm serializing the entire application. So I will record 3E7. The better solution would be to create thread private containers. And one way I can do this is by creating an array here. So what is the container? What do I need the container for? For this array. This array is of type int and it has m elements. So I will call int hist private of size m. And then when I begin the parallel loop, I will say that this is first private. So the reason I'm using first private is that I want to initialize this variable to the same value as it has outside of the parallel region. So outside of the parallel region, I'm initializing it to 0. And then I'm not just creating a copy for each thread, I'm also initializing it to the value outside of the parallel region. So now, instead of incrementing hist, I will increment hist private. And actually, before I even do that, let's see, can I use the built-in OpenMP functionality? We discussed reduction. And reduction is a built-in functionality in OpenMP for exactly what we are trying to do. When I build, it says, no, cannot use pointer or reference in the reduction clause. So OpenMP will not help us. We have to do it by hand, and this is why we do first private hist priv. So here, to avoid the race condition, I will use hist private. And in principle, this will compile. It will even run magnificently fast, but it will produce incorrect results. The result is 0. The result is 0 because, well, I never touched the original array hist, which I have to return. Right? This, where is it? This array, I never touched it. So I have to aggregate the results across all threads, and there is no way that I can do it from within the main for loop. So I will have to split this pragma into two pragmas. And what I'm doing, you can do in C and in C++. So from the first pragma, I remove parallel. I remove the word for. From the second pragma, I remove the word parallel. And this does not apply anymore. And I create a scope inside of pragma OMP parallel so that the compiler understands what's going on where. So now I have an equivalent code, but now I have an option to put some code here. Where is that? So I am still inside of the parallel region, but outside of the main for loop. So here is where I will put reduction. And the reduction will look like this. Hist 0 through m, increment by hist private 0 through m. It should work, right? And it works fast, but the results are incorrect. The results are incorrect because I still have a race condition here. I have fewer race conditions, but they are still messing with my results. So I need to protect this. One way to protect this is maybe put pragma OMP critical around this whole thing. This is brute force, but it might work. So this is the performance on the host, 5.2 E9 performance on Xeon Phi. Five point four E9, 5.2 E9, 1, 10. So this is the optimized performance, where we did not, we were not too careful about reduction. Let me try to implement a slightly more lightweight mutex for this synchronization, and that's how I will do this. So instead of critical, I'm using atomic. But atomic, I'm only allowed to apply to a single operation. I cannot apply atomic to a loop. This is why I have a loop around it. Let's see if that changes results. Oh, there's actually, well, there is fluctuation, so I can't really tell if it's worse or better. My claim is that this should be faster, but whether or not we will see it depends on how much work we have in the main loop. So for smaller data sets, a more efficient reduction would be more noticeable. Looks like on Xeon Phi improved performance quite a bit. So thread private plus pragma OMP atomic. On the CPU it's the same performance. On Xeon Phi it's 1.310. So we got 30% more on Xeon Phi by using a more lightweight mutex. So that's good. We were able to improve performance on both platforms. I would not compare Xeon Phi performance against the CPU performance because they are actually from different classes. I have an inexpensive 12-core CPU, which is no match to Xeon Phi, neither in the thermal design power nor in the costs. So also I want to point out that this problem has both bandwidth bound and compute bound components. But let's see what else we can squeeze out of this calculation. We were able to implement multi-threading and to do it efficiently. How efficient is it? Well, this versus that is almost a factor of 100. So I'm close to where I want to be, but this application has a memory bandwidth bound component to it. So I should not really expect to scale by a factor of 114 like before. 114 is double the number of threads. So what else can we squeeze out of it? And in the presentation, I talked about false sharing. And this is what I will try to demonstrate now. False sharing, a reminder, is a situation that occurs when we have more than one thread modifying the same cache line. And I'm going to run into this situation when I make an attempt to be more economical about my thread private containers and stick them too close to each other. So this is what it will look like in code. I have this hist private which I replicate across all threads. Instead, let me create hist global m. So hist global will be different. It will be a two-dimensional array, and the first dimension will be equal to the number of threads. How am I going to get the number of threads? There is an OpenMP support function, OMP get max threads. Notice that there is also not OMP get num threads. The difference is that this works outside of a parallel region and returns the maximum number of threads that you can run. That one works only inside of the parallel region, and it returns the number of threads that you are currently running, and it may be less than the max threads. Actually, outside of the parallel region, it returns 1. So this is the correct value. I have hist global. Now, when I enter the parallel region, I will allow every thread to find its compartment, and this is how I will do this. So now the thread private container will be a pointer to what? To hist global my thread of 0. And how am I going to find my thread number? I will call another OpenMP support function, OMP get thread num. Also notice that it's easy to confuse this function with that function. This is the number of the current thread, and that would be the count of threads in the current parallel region. So let's see if that compiles. I forgot a semicolon somewhere. Oh, the problem is that first the compiler does not know where what OMP get max threads is. The semicolon, thanks for the hint in the questions, I forgot here, but the compiler doesn't know this function or that function. To tell the compiler where to look for them, I have to include the header file omp.h. In Fortran, similarly, I have to use omp.h. Use is the Fortran keyword. So compile again. And now the compiler thankfully detected this bug for me. Hist private cannot be among the first private list. It's actually not declared. So I actually have to remove it because I want hist global to be shared across all threads. But hist private will be compartment of this thread. Let's see if I can compile. Now the code compiles, and let's see what happens when it runs. It produces incorrect results, which means that I have a bug. So let's oh, this is what I meant. So this is array notation. I am initializing a two-dimensional array with zeros, and in the past I did not have proper initialization. Okay, so now the code runs, and let's compare this performance to the performance that I had before. So the code is now hist global. On the CPU, I get 8.3E8. On Xeon Phi, I get 1.3E9. Is that right? I should be able to strategically place this here, so I don't have to switch back and forth. Yes, 1.4E9. Now notice that the performance went down by a factor of 10 from this implementation, and almost a factor of 10 on the host. That I'm claiming is because of false sharing, and I can detect false sharing in my case by just looking at the code. Where am I writing to memory? Here. What is that? Well, that is this. Okay, so different threads have different addresses. How far apart are they? Look here, and they are m elements apart, where m is only equal to 5. So I've run into this situation. Now let's pad the inner dimension. And I will choose it like that. M padded, I will set equal to m. Actually, yeah, I will set it to m plus. So I want to make it a multiple of 64 bytes. So I will make it m plus. How many bytes do I have to? Let's introduce also in padding elements is 16. So I will put I think this should work. So what I will change in my code is here I will choose m padded. I actually don't have to touch all these other elements. I don't even have to initialize them. I just have to have them there. So when I do that, performance on the CPU increases slightly. On Xeon Phi, it should just fully recover. So I don't know if this is a significant difference from that, but this is close enough. But clearly on the host, the performance is worse than before I converted the data container. And I can fix this by trying more padding. With more padding, I get higher performance. With even more padding, I should get even more. Actually, this did not change. Nope. Well, there's a lot of fluctuation. To fix this fluctuation, I would actually have to use thread affinity, but for now, we can just notice that, well, I'm getting somewhere close to where I need to be. So padding helped us to recover performance. And just out of curiosity, let's see what happens when I fix affinity. We will discuss affinity in the next episode, but what I have to do here is, in the make file, I have to set kmp affinity equals scatter. And potentially, I could also, yes, you can see on the host it improves results quite a bit. And if I set the number of threads to 12, I might get even more. Yep. So let's record this just for fun and giggles. So with just affinity scatter, I got something like 6 E9, and OMP num threads 12, I got 7.4 E9. So on Xeon Phi, the same might work, might not. Well, this will not change results because this is the default affinity on Xeon Phi, but I can tune the number of threads. KMP place threads, I can try 3 threads per core. Space. So 3 threads per core instead of 4 threads per core. Actually, this makes things worse. I can try 2 threads per core. This is just a preview of what we are going to focus on tomorrow. This is even worse, and 1 thread per core is probably going to be yet worse. So on Xeon Phi, affinity settings were optimal to begin with. On Xeon, we were able to optimize performance slightly more by controlling thread affinity. All right, if you have any questions about this example, type them in, please. And while you're doing that, I am going to switch to the next lab. So I've squeezed out all I could out of this lab. I've demonstrated this parallel pattern that we've seen before, but I think it is very important, so I wanted to emphasize it once again. Create thread private containers, use them to avoid race conditions, and then use lightweight mutexes to do reduction. Sometimes you may need to worry about padding between your thread private containers, and you might want to optimize thread affinity, depending on the type of your application. So that said, I will go to lab 405. And once again, it has the main function and the worker function. And we are going to focus on the worker function. And to give you an illustration of what we are dealing with, this is the problem. This is a synthetic application, but I promise that you will see this exact problem occur in a more realistic calculation when we talk about memory optimization. So I have a matrix, and I want to go through all the columns in this matrix, and I want to sum them up and return the result for every row. So in code, it is easy to express. I have this matrix. Here are the dimensions of this matrix, and this is the result that I want to return. What I'm doing is I'm setting up 2 loops. One iterates through the rows, and then for each row, I'm going to run through the matrix, do the summation. I expect the compiler to vectorize this inner loop. And when I begin when I begin working with this code, first I will obtain the baseline performance, but then I will see where I have to optimize. So the baseline performance is 37 gigabytes per second on the host and 9 gigabytes per second on the CPU. I'm measuring performance in units of memory bandwidth. So creating a new log. $38.9. So as usual, let's see if we need to worry about something in this code. I will start by studying the optimization report file, and it says OpenMP defined loop was parallelized, and then in line 22 it says loop was vectorized. Of course, it also has this remark peeled loop and remainder loop. I actually probably don't have to worry about it at this point, because if I look in main, I will find that n is very, very large. So even if there is some peeling at the beginning of this loop, there will be so many iterations after it that it will compensate for, well, the peeling will be insignificant. As for m, it is equal to 4. This is where I could potentially see the problem with my eyes, but I can also detect this problem with a scalability test. Let me set the number of threads to 1. I will edit the makefile to do that, and I will set OMP num threads to 1, and here OMP num threads to 1, and run again. So this is a thread scalability test. And I will record. One thread on the host gives me 14 per second, and on Xeon-Phi 2 gigabytes per second. Now, is that good? What did we expect? Did we expect 2 times? Did we expect 12x on the host and 2 times 57x on Xeon-Phi? And my claim is no. This speed up you would expect from a compute bound application where you are limited by how fast you can crunch the math. This is not a compute bound application. For every memory access, you are doing just one arithmetic operation. And if you remember, well, the theoretical peak memory bandwidth is a few hundred gigabytes per second on Xeon-Phi. The theoretical peak performance of vector processing units is, well, 1 terabyte per second, teraflop per second, which amounts to 8 terabytes per second. So if you are reading a large amount of memory and doing just one arithmetic operation, it is free. This arithmetic operation is free, and you are limited by the memory bandwidth. We will talk more about this in session 9, but I just wanted to point out that we do not expect this. Actually, we expect for a bandwidth bound calculation on the CPU a speed up by just under 12, on Xeon-Phi something around 8x. And 8 is the number of memory controllers on Xeon-Phi. But what we got, the speed up due to parallelism, was only 3 on Xeon-Phi and less than 3 on the host. So on the host we had what, 2.7, 4.5. Did it do the math right? Yes, 2.7. Okay. So this is what we got. We expected, well, just under 12 on the host, and we expected 8x on Xeon-Phi. So this is telling us that even for a bandwidth bound application, our code does not scale well. And this is what we can use to see, okay, too few iterations here. So let's try to improve this. I don't have enough parallelism to scale across all of the threads that I have, across all of the memory controllers even that I have. So I need to change something. Well, I know that n is pretty large, so why don't I move Pragma OMP parallel 4 into the inner loop, where I have a lot of parallelism. Now to make this correct, I will have to use reduction, and I'm doing summation on the variable sum. And let's see what happens when I compile. It compiles. let me look at the vectorization report. I want to know something about loop in line 21. Actually says loop was vectorized, so the compiler was able to make vectorization and multithreading coexist in this loop. Okay, let's run it. So the performance, oh, and I apologize, I forgot to remove the scalability test in the make file. Compile again, this time with flag-b to really recompile, run on the host, and run on Xeon Phi. So I got 25 and 88. So parallel inner loop gets 25 gigabytes per second on the host and 88 gigabytes per second on Xeon Phi. So this is not comfortable to me. On Xeon Phi, we seemed to improve the performance by an order of magnitude. This is good. But on the CPU, the same optimization reduced performance. So I know that something is not right with this code. And what's not right is that I start and stop my threads many, many times. Well, not many, just 4. But that's enough. And also, I'm not exposing all of the parallelism that I have to the application. So different loops will run with different patterns of memory access. Yeah, this is not going to end well. Instead, I would try to expose all of the parallelism that I have in this code. And I know that potentially I can do it with loop collapse. So why don't I go here and try to say naively, well, just collapse 2 loops. Meaning that I want to collapse this loop with that loop. If I try to compile this, the compiler will say, sorry, you have this code between one loop and the other loop. But if you want to use loop collapse, they have to be perfectly nested, meaning that one should immediately follow the other. You cannot have any code between them. How do I do it so that there is no code between them? Well, potentially I can move this out. And now, can I use just the reduction clause? Well, probably no, because, well, you see, different threads can be operating on different values of j. So maybe I will have to make it an array. And then I will use first private sum. I cannot initialize like that. I can initialize like this, and then I will do this. Is this going to work? Well, possibly, but there is a race condition. So what is the problem? S of I. Oh, yes, of course. Now I have a complete mess of my application. I have these two perfectly nested loops, but then I may not have this here. Where does this line belong? It well, maybe what I need to do is yeah, it's all becoming a mess. I cannot just proceed like that. So if I want to use loop collapse, I will probably have to once again split the parallel region clause from the for clause. So I will remove for here and collapse. And I will remove parallel from the next line and first private. And this allows me to insert parentheses. So that I move the scope of, that I have separate scope for Pragma OP parallel. So this line 29 is still inside of the parallel region, as you can see. This is all inside of the parallel region. Okay, so now I can probably do this. This is my reduction. And to protect this from a race condition, I will use pragma onp atomic. This is a familiar pattern. Once again, we start the parallel loop. We use this first private to create a private copy, or instead of doing that, we could move this entire code in here. But I used that so that Fortran programmers can understand how it works. Then we have a parallel loop where I'm using loop collapse. And then I'm reducing from thread private containers into the result. Does it work? Illegal operation in atomic expression because I need to do plus equals. Now it works. But results are incorrect. I think the results are incorrect because I forgot to initialize some S. Okay, now results are correct. But performance is not encouraging. On the host, I get 16. On the on-file, I get 7. So things got worse. And the optimization report gives me a hint what happened. What happened is, let's look at lines 24 through 27. Yeah, 24 was not vectorized. 27 is not even in the picture. Basically, vectorization failed, and I have no idea what the compiler is doing here. To fix this, I suggest that we simplify the compiler's work. This loop has a lot of iterations, and we don't need all of these iterations to be collapsed with the outer loop. We could afford to do just a few iterations here in the innermost loop. So we will do strip mining. So I'm writing an equivalent code. It is equivalent as long as strip width is as n divides into strip width. So let's do that. I introduce a strip width, and I will set it to something that is a multiple of 16. Well, for example, 1600. Actually, let's begin with 16. And then I will do a check. Assert n modulo strip width equals 0. This is just for convenience. In fact, instead of doing that, I could write remainder loop and it would work. So let's see what happens. The code compiles. It's slightly more happy on both platforms. So it looks like we are on a good track. But like with any code with an arbitrary parameter, I have to check, did I make a good guess for this parameter? 61. So let's try to make this bigger, and I will make it, for example, 64. So this is making things worse. On host, better on Xeon Phi. And also I can recognize that here the loop is now very short. So I might want to take advantage of pragma vector aligned. This will be justified as long as the matrix itself is aligned. Plus, this is a multiple of 16. It will drop the peel loop and I may potentially get better performance. Indeed I do. And now I can get slightly more aggressive, and just from experience I know that going to even higher values of the strip width will give me yet better performance. Well, it looks like it's saturated. So on the host I'm getting 40 on 41 on Xeon Phi. I'm getting 112. So looks like this was the optimal solution, collapsing the outer two loops, and this allows me to have vectorization in the innermost loop. Yes, you can see that the loop in line 32 was vectorized. This is not bad. And let's see if now the scalability test is satisfactory. So I will go and edit the make file again, and I will change the number of threads on the CPU to 1, and on Xeon Phi also to 1. So on the CPU I got 14, on Xeon Phi I'm getting 3.5. So speed up. Here the speed up is 3, and there the speed up is 30, so 32. Yes, 32. Okay. So we expected yes, I may have been too fast to claim that the expected speed up is 8 here. I need to do my homework and revisit this topic, but it looks like we are on the right track. The number that I want to compare the performance with is the benchmark of the stream benchmark on the respective platform. The stream benchmark on the host gives me around 60 gigabytes per second, on Xeon Phi around 130. So now I see that on the host I'm obtaining something like 70%, and on Xeon Phi something like 80% of the theoretical peak bandwidth. And I can improve this some more by playing more with this tuning parameter. I can also try to tune affinity. So on the host I can set affinity to compact and the number of threads to 12. I'm sorry, not compact, scatter, because this is clearly a bandwidth bound application. So on the host I can get 59. On Xeon Phi I can also try to tune affinity and do something like KMP place threads equals maybe 1. Actually, let me record this before I go too fast. So on the host I get 59 gigabytes per second. So this is more than 90% of the stream bandwidth, so I know that I'm close to where I want to be. On Xeon Phi this may not be as trivial because with bandwidth bound calculations sometimes you have to tune also, I got the little T. Sometimes you also have to tune prefetching. And in addition to that, sometimes maybe the value of this tuning parameter is optimal on Xeon Phi with a different setting. But I can double check if I did a good enough job also by going to solutions. Looks like the solutions have the same, so I don't think we moved farther than that with our optimization. But anyway, we achieved 59 gigabytes per second on Xeon Phi versus unoptimized 38. We achieved more than 110 gigabytes per second on, I'm sorry, this was on Xeon. This versus that on Xeon, and then on Xeon Phi this versus that. And we did it using two techniques: strip mining the inner loop and collapsing the outer two loops to expand the amount of parallelism visible to OpenMP. Of course, to make this program correct, we had to use a lot of other techniques that we discussed earlier. We had to use thread private containers and mutexes to run parallel reduction, but you saw once again that this was a very useful parallel pattern. So this is what I wanted to demonstrate with this last lab. And if you have any questions, feel free to type them now or a few minutes after I end the broadcast. Hope you enjoyed this, and hope to see you again tomorrow, where is that correct? Yes, today is Thursday. See you again tomorrow for the second part of the discussion of optimization of multi-threaded applications. Thank you very much for your attention. See you tomorrow. Bye.